As we mentioned earlier, that suppose that we have the cache. Here you have the data, you have the tag, and you have the valid bit. And in this cache size, it's actually from 0 all the way to 1023. So you have actually 1024 different locations or different floors or different blocks. And we would like to see like how we can address this particular cache or this particular hotel, for instance. It tells you also that actually this size is 32 bits. We would like to know how many different addresses we can actually get from these 32 bits, or how many rooms we can generate from all of these 32 bits. We also mentioned earlier that our processor with the memory is byte addressable. So basically, the lowest that you can address is byte. You will not be able to address a bit, but you can address a byte. So the lowest will be byte. So I need to see how many bytes can I generate from these 32 bits. It's just 32 divided by 8 will give me 4. So I can actually create 4 rooms in each of the floors from these 32 bits. So first, I would like to see how I can address a room in a floor. I have here 4 rooms per floor. This is a floor. I have 4 rooms. How many bits do I need, or how many digits do I need to address 4 different locations? It's just 2 bits will be enough. 2 bits should be enough, which is basically here. Very first and second bits. Here is 0, 1, all the way to 31. So I have 32 different bits. So the very first 2 bits will just to address my room number. Then the next thing is I would like, so I specified as an example that this is the room, but I didn't specify that this is the room in this floor, or in this floor, or in this floor, in which floor. So I have to specify also in which floor, or in which block. How? I need to see like how many bits do I need for the 1024 different blocks or different floor. So log to the base 2 to this, it will give me 10. And that's why here the next 10 bits will be for the block number or the floor number. Anything afterwards will just be the tag in this particular case. So 32 minus 10 minus 2, it will give you 20 in this particular example. If you recall, with the example with the hotel that we gave, and we mentioned if we have 10, 12, and this 12 is just the room number, and this 10 is the floor number. So as you can see, we always begin here with the smallest thing, which is the room number, and then we go to the highest or the other thing, which is the floor number. And that's why here, with the very first 2 bits, we specify either this or this or this. It's just the room number. And then the next most significant bits, then it will specify the floor number and so on and so forth. In this case, in the example that we had earlier, that we are in the 10th floor and we would like to access room 12. So it's 10th floor and the room 12. In this case, this will address my room. This will address, will address my floor. Or if you will, this will address my block number in this particular case. I've also mentioned that if we have a multi-word block, in this case, I don't have only, I don't have only one of these. No, I might need actually multiple of these. So I may need to specify a room number, but also a direction number or a building number or whatever the thing is. This is the case here. So I have here, so let's say that this is one building in my hotel, this is another building, and another building, north, south, west, east, and so on and so forth, as an example. So I have to specify first my room number. Again, this is 32. Each one of these is 32, so this is 32. Again, I can have here 4 rooms inside my ward or inside the first building. So I have to specify first the room number. The room number, how many digits do I need to specify a room number? Again, 1, 2, 3, 4 different locations. So I just need 2 bits. And that's why the very first 2 bits will just be for my room number or my byte offset. What is the number of bytes? It is the first byte, second byte, third byte, fourth byte. But I didn't specify right now if I am here, or I am here, or I am here, or I am here. Which building I didn't specify. So I have to go a little bit up to specify the building. So I have specified the room. Suppose that I'm specifying this room, for instance. I need to specify that actually this room is in this particular building, not in the other building. So we have how many buildings? 1, 2, 3, 4 buildings. How many bits do I need to differentiate between these 4 buildings? I just need 2 bits. So that means that the next 2 bits will just be for the block offset or building number, for instance. So at the very beginning, I specify the room number, then the building number, and then, of course, the floor number. So after that, I need to specify a floor number. So I have specified, for instance, this room, and this room is in this particular ward, on that particular building. I need to specify which floor, that particular floor. How to do that? We have here from 0 to 255, so we have here 256. Again, log to the base 2 to 56 is equal to 8, and this is what we have here. We have 8 bits to specify the floor number. Anything after that will be the tag. 32 minus 8 minus 2 minus 2 will give you the 20, which is this. Because when I specify this, for instance, I specified the room, I specified the building, I specified the floor. So I knew everything about the location, but I still didn't specify you. In order to specify you, as opposed to all the other guests that basically were in that room as well, but maybe in another day, I have to specify the tag. For instance, with this example, the tag might be the date that you actually were there. So then I can specify exactly you. This is the tag in this particular case. Again, if this is the whole 32, so that means, of course, that this will be 20. But suppose that this is even bigger. If it is 64, of course, again, this will be bigger and bigger and bigger and so on. I might specify the date. I might specify the check-in time. I might specify the check-out time. I might specify a lot of other things more to specify that this is you, not any other one. We have highlighted that suppose that we had this cache, for instance, and with this cache we have 4 different floors, and with each of these floors, suppose that I am just addressing one room, and we showed that if the processor is accessing any of these rooms or any of these addresses, how exactly I will face the miss and how exactly I will face the hit, as we have touched it previously. Also, with all of these, we need also to specify the tag, as you have seen previously, to mention or to highlight that that's exactly what I need to access, not any other data that it might have the same location as well. But this scheme is just 4 floors with 1 room for each floor. Suppose that we need to change the scheme or the distribution. Suppose that I would like to change the design, and instead of having like that, I need to do it as an example like that. So still I have 4 rooms. This is 1, 2, 3, 4. But instead of 4 floors, now I have 2 floors. And again, 2 floors, and again also I will add the tag here. So now how this will affect my miss or hit rates, how this will affect my performance, how this will affect the accessing of the data inside the memory, and so on and so forth. This is what we would like to highlight. Just before we go to that particular case, just to remind you that in this particular situation, we have 8 requests and we have 6 misses in this particular case. Suppose that we have this situation or scenario that we just mentioned. Instead of having 4 floors, with each floor 1 room, now we have 2 floors, and each floor has 2 rooms. The most important thing that we need to think about is how I will address that. Because how I will address that, it will specify exactly, it will help me into the specific location of any of these particular addresses that I'm intended to access. So how we can do that? Again, we will think with the same way. We have 2 floors and we have 2 rooms. If we have 2 rooms, how many bits do I need to specify one room from the other? Just 1 bit, because 1 bit I might say 0 is the right, 1 is the left, or the other way around, or this is 0 and this is 1. So as an example, I can say that this is 0 and this is 1. With the floor number, again, I have 2 different locations. So again, I just need 1 bit to specify each of these locations. So again, I have 0 and 1. So that means that if someone is here, I can say that that one is in room 1, floor 0. So room 1, floor 0. And we, as we mentioned, we specify always the room first, or the lower place first, and then we go up higher and higher and higher and so on. So if I have 1, 0, so this means that it is located here. If it is here, it's basically 1, 1. The last 2 bits. Correct? Because now 2 bits just needed to specify the location inside the hotel. You just need 2 bits. 1 bit for the floor room number and the other bit for the floor number, and that's it. So that means that any address that I will get, I will just need to look at the very first 2 bits. One will give me the floor number, or one will give me first the room number, and the other one will give me the floor number. And of course, here I will just have my tag. Okay, so let's go over these step by step as we have done previously in the first scenario. Here, the 0, again, the 0, how we will write the 0, it is 0, 0, 0, 0. We need to look only at the very first 2 bits. The very first bit, it will give you the room number. Yes, or the ward number, for instance, or the block offset. And then the second number will give you the floor number, or the block number, as well. 0, 0 means that you will go to 0 and 0. You will go to this particular location. You didn't find memory of 0 there. So what you need to do is just to bring memory of 0 from the lower level and copy it to the higher level. If you are searching for the cache, so it will come from the main memory and be copied to the cache. But interestingly, there is another idea that would be exploited in this particular case. If you recall, we mentioned that there is something called the spatial locality. Would like to remind you of the spatial locality. Spatial locality means that you actually bring with you from the lower level the data that is adjacent to the data that you are frequently using or that you are using. Remember with the example of the library, when I mentioned that you will go to the library and then bring, for instance, the textbook that is corresponding for the subject that you have an exam tomorrow or after tomorrow, something very close. Just to be in the safe side, you might find other textbooks with similar name close spatially in the library at that particular location, correct? What you need to do is what? Just bring with you all of the things that you might think would be helpful for you, correct? So you not only go and bring, because you know that each time you would like to go to the library, you have to pay a lot of money and time. The least will be just the time, correct? So you might need to walk 15 or 30 minutes to the library. So just to be in the safe case, you'll bring all the textbooks with you that you think it might be helpful. Just to increase the probability of not missing anything or decreasing the probability of missing. In this case, we're applying the same. So when we will go to bring memory of 0, and since memory of 0 is in the spatial locality in the same floor, we'll bring all of the things with the same floor. So I will bring with me memory of 1. Why memory of 1? Because basically memory of 1, if you write 1, 1 is basically 0, 0, 0, 1. So if you look at the very first 2 bits, the room is 1, the floor is 0. And this is basically has a room of 1 and floor of 0. And that's why this is has the lower 2 bits as a 0, 1, as you can see from here. Room 1 and then floor 0. And of course, since you didn't find the data, you already miss. And you write the tag is just 0, 0. Let's copy these things to the next snapshot in time. So you have memory of 0, memory already of 1, and you have 0, 0. The next thing right now, you would like 1. We mentioned that the location of 1 will be at room 1 and floor 0. And this is basically that location. Interestingly, you find that you already have the 1 because you brought that from the previous step. That's why in this situation, you actually hit. Copy that to the next snapshot in time. And then you have memory of 0. And this is 0, 0. But in this case, you need 2. How you will write 2? It's 0, 0, 1, 0. So it is in room 0, floor 1. Room 0, floor 1. So actually, you are looking at this. Did you find memory of 2? You didn't find memory of 2. So actually, you missed. You will bring a memory of 2? Yes, you will bring a memory of 2. But with the same idea, because of the spatial locality, you will bring the 1 afterwards, which has actually the room 1 and the floor 1. In this case, the very lowest 2 digits will be 1, 1, which is basically memory of 3 in this particular case. And again, the tag will be 0, 0. Copy again whatever I had earlier. So this is here memory of 0, memory of 1, memory of 2, memory of 3, and then tag 0, 0, and 0, 0. In this case, I am asking for 3. 3 again, as we mentioned, 0, 0, 1, 1. So floor 1, room 1, floor 1. So basically, you are looking at this particular location. And interestingly, it is there. So you basically just hit. Copy all of these again. But in this case, you need 4. How to write 4? 4 is basically 0, 1, 0, 0. So if you look at the very first 2 digits, it's room 0, floor 0, room 0, floor 0. That means that you are looking at this particular location. When you went there, did you find memory of 4? Memory of 4 is not there. You find instead memory of 0. So you actually miss. That's why you need actually to override that by memory of 4. But when you override that with memory of 4, or when you will go and bring from the lower level to the upper level memory of 4, again with the spatial locality, you will bring the 1 beside to that. And when you bring the 1 beside that, actually you will bring also with you memory of 5, and then you will update the tag that is basically 0, 1, which is the tag for memory of 5 and the memory of 4. Now update or rewrite whatever you had in the previous memory of 4, memory of 5, and then memory of 2, memory of 3, and this is 0, 1, 0, 0. Now you would like to get the 3 again. You will go here, you find the 3, so you actually hit. Copy everything again, memory of 5, memory of 4, memory of 2, memory of 3, 0, 1, 0, 0. You would like to get the 4. Interestingly, the 4 is here, so you again hit. Copy everything, memory 5, memory of 4, memory of 2, memory of 3, Now we need 15. How we write 15? It's 1, 1, 1, 1. So we need to go at room 1 and floor 1. When you go at room 1 and floor 1, you actually would like to access this one. When you went there, you didn't find 15, you find 3, and that's why you miss. So you will override this and put the 15. But again, with the spatial locality, you need to bring the one that's supposed to be here, which in this case, it has to be memory of 14. And again, we'll override the tag with the new tag, which is basically 1, 1. So among all of the requests right now, I have how many misses? 1, 2, 3, 4 misses. If you recall, here I have 6 misses, in this case 4 misses. It's not always guaranteed that this will be the case. However, we might increase the probability of hitting or decrease the probability of missing by having this kind of an ID. So here is just showed you that the same thing that we have mentioned as we indicated, 8 requests with 4 misses in this particular case. So we have another expression here is called write-through, a scheme in which writes always update both the cache and the next lower level of the memory hierarchy. So what does exactly mean? So now, if I would like to update an information in the cache, for instance, as a processor, should I update only the cache, or should I update the cache and the memory as well? This is an important question that we have to ask ourselves and find a solution to that, and which one would be better, because there is trade-off. If I would like to update only the cache, there is a benefit of course, the waiting time will be a lot less, because I will just interface with the cache, update the cache. I don't need to worry about the main memory, and that actually will increase my throughput, correct? And reduce my waiting time or my access time. But what is the drawback? The drawback right now that there is a mismatch between the cache and the main memory. There is a mismatch between the cache and the main memory. So then, in order to avoid this mismatch, I need actually to write for both. I need to write for the cache, I need to update the cache, and I need to update the main memory. But in this case, I am paying what? The stalling or the waiting time, because I need just to wait until I update the main memory or the second level. And this is what we call it write-through. Write-through, it will update both the memory, main memory, and also the cache. Both of them, the cache and the main memory as well. Let's see here an example to just highlight the effect of doing something like that. Suppose that I have a base cycles per instruction CPI is equal to 1. And 10% of my instructions are stalls. What does that indicate? This indicates that actually 10% of my code is accessing the memory. So 10% of my time, I would like to access the memory. And it also gives you here an information that write to the memory, it takes 100 cycles. Each time I would like to go to speak to the memory, I need to pay 100 cycles. So what would be, in this case, the effective CPI? The effective CPI is equal to the base CPI, which is 1, plus 10%, which is the number of instructions that is dealing with the memory, 10%, multiplied by 100 cycles, which is the penalty for accessing only the memory for one time. At the very end, my CPI, effective CPI, increased to 11 instead of 1. It was 1, and now it is 11. You can see like dramatically increase in my CPI with just having this idea of write-through. Just to give you a sense, or just to feel how these things will affect negatively the performance. Suppose right now that I am introducing the slides. Suppose that I'm introducing the slides. And just normally, usually when you give a presentation, just normal presentation, you might give like a slide would be taking about 1 minute. So my base slide per time is 1 minute, correct? Slide per 1 minute, correct? So my CPI, let's say my CPI will be 1 slide per 1 minute. But suppose that one decide that each time I'm finishing the slide, I have to check with each one of you if you did understand the slide or not. So I introduce the slides and then I ask, did you understand? And I send a request and then wait for the feedback. And then go to the next one, send the request and then wait for the feedback. Send the request and wait for the feedback until I finish all of you. Then after that, I can go to the next slide. What would be my effective right now? Slides per time. It's not 1 minute. So suppose that I will take 15 minutes for you to check, and I am already have 1 minute for myself. So 1 plus 15. So my effective slide per time now, it is 1 slide per 16 minutes instead of 1 slide per 1 minute. How many slides do I would be able to finish in one class? My performance, of course, went down. Okay? Dramatically down. How can we alleviate or solve this issue? For instance, I might say, okay, I need, instead of send a request for every one of you, after finishing the slide, I will ask if anyone has a question or not. Then it's just broadcast. And then as soon as you have a question, you might raise your hand and then we'll take the answer in case you have a question. So of course, this on average will enhance my CPI or my slides per time, for instance, as a whole. Can we do better? Can we even enhance my performance? Yes, I might say as an example, for instance, I will not ask any one of you if you have a questions or not after each slide. Instead, I will say that as soon as you have a question, just raise your hand and then I will answer when appropriate. Or maybe before that, I might say that instead of just asking if you have a question after each slide, I may say after 2 or 3 slides, I will ask that question. So then again, increasing my performance and reducing my CPI, if you will, in this case. The better things, or even not to ask at all, is just to say that if you have a question, just raise your hand, and then I will answer when appropriate in this case. Of course, with each of these steps, I am increasing or enhancing my performance. And that's why in the right through, as you have seen, the CPI went from 1, the normal case, 1 slide per minute, to all the way till 11 with this kind of idea. They came up with a nice solution that will solve a little bit and will enhance a little bit this effective dramatically decrease or increase in my effective CPI by using something called write buffer. This write buffer will just collect all of the queues that you would send to the main memory. So suppose that I am the processor, I will send to the cache, update the cache, and I will update the main memory, but instead of sending it directly to the main memory, I am sending it through a buffer. So that means that when I send it, this is my cache, I am interfacing with my cache, this is my main memory, I am sending this through a buffer, and then it is like that. So I am feeding very quickly the stuff here with my CPU, adding, and it is draining, if you will, from the other side to the main memory. Of course, I am expecting, or I knew already, that the flow rate here is a lot higher than the flow rate here. So I may fill until it's totally filled. At that time only, I have to stop. At that time only, I have to wait until the main memory is updated. Before that, as soon as I have the buffer, it's just waiting, just send anything to the buffer and so on and so forth. It is the same exact idea when you have a sink. When you have a sink, and this is like the tap water, the flow here, and there is, of course, a sink of flow draining here the water. You fill until the very end. That might be split afterwards. You have to stop. At that time, as a processor, this is the flow rate of the processor. You have, of course, to shut down that one. Otherwise, the information will just be lost. So this is the same concept. So the idea of the buffer, it's actually, of course, solving the problem of the waiting and enhance the stall or waiting time in that particular example. Okay, so this is if I would like to write through, which is updating the cache and the main memory. Suppose that I don't want to do that. Suppose that we have another idea that's called write back, which I will only update the cache. So right now, I don't want to update the main memory. I don't care about the main memory. I just would like to update the cache. But unfortunately, this is dangerous. Of course, it gives me a lot of benefit in terms of the time, but I'm losing another thing. There's trade-off. I'm losing what? I'm losing the consistency between the main memory and the cache, because now the cache is already updated, but the main memory is totally off. It's not updated. There is inconsistency. So how we can solve this problem? Because I can't just like omit one of the benefit and just get rid of one of the benefit and just took the other benefit. I need to take both of them. So how we can solve that? They came with a nice idea. They said, okay, that's fine. When you update the first time the cache, just work with the cache. However, if you would like to update or re-update the same location another time, only at that time, please, you have to update the main memory. Otherwise, there will be like extremely inconsistency between the cache and the main memory. Again, I update the cache memory the very first time. This is I'm updating the cache. I don't need to update the main memory. But then later on, I would like actually to update again the same location of the cache. Then at that time, please take that data to the main memory only. But then the next question is, okay, so how I will know? How I will know that this data is already updated or it's not updated in the main memory? They said, okay, that's fine. We can have what we call dirty bit. This dirty bit will hold this information. It will tell you if this needs to be written back to the memory when it is evicted or not. Only in this particular case, you have to update the main memory. So again, this is my cache. This is my main memory. At the very first time updating, no update to the main memory, no need. The second time you update the cache memory, then please take the data, update the main memory in this particular case. And then only in this case, you need to stall or to wait. Can we do better? He said, yes, that's fine. We have the idea of write buffer before. Why not use it here as well? So even in the case of the second update, when I need to wait to the main memory, why not to add the write buffer here as well? This case, this will be my write buffer, and it will hold the data, and it will also reduce my waiting time in this particular case. So this cache situation, if I have a cache hit, for instance, just the CPU will proceed normally without any problem. But if I have a cache miss, as we mentioned, I just, of course, need to wait or to stall the pipeline in this particular situation and just fetch the block from the next level to my close level in this particular situation. If I have an instruction cache miss, just restart the instruction fetch. While if I have a data cache miss, just complete the data access in this particular case. Now we would like actually to highlight what would be the sources of the cache misses. And this is extremely important. And I would like each one of you to be aware of all of these example of sources, and also when it happened and how it can be solved. The very first one is called compulsory miss. What is a compulsory miss? This actually happened at the very beginning when you just, for instance, just restart the computer. Or it will be the very first time that to access these data and so on and so forth, with very high probability that you will miss. Because when you restart, you have just garbage data. There is very high probability that the data that is there is not what you are intended to. So that means that with high probability, it will be rubbish, and that's why you will miss. This is under the compulsory miss situation. How you will solve such a situation or such a scenario? You might say, like, I mean, I won't be able to do that, just restart and I just need to pay that. Yes, that's correct, but there is an idea that will reduce the miss rate with time. They said, okay, increase the block size. Why increase the block size will help the compulsory miss? Because with the same idea of a spatial locality, you have to bring all the block offsets that is inside the very big block, correct? You have to bring all of them. Suppose that you just missed from the very beginning, the very first one, but you will bring all of the others with them. So the next time when you would like to access something with this idea of spatial locality, there is a probability that you will use one of these things in the same floor or in the same block. So increasing the block size will decrease a little bit the compulsory miss in this case. Okay, that's fine, but what is the drawback? What is the drawback, or one of the drawbacks? We'll mention other drawbacks for this, but one of the drawbacks of increasing the block size is basically the miss penalty. What does that mean? Suppose that you are going to the library and you would like to bring one of the textbooks, correct? And because of the spatial locality, you have decided that you will bring the text that is close in terms of the titles or the contents with you, correct? You decide to bring 2, another one decide to bring 3, another one decide to bring 15. Who will pay more in terms of time and money? Or suppose, forget about the money, just time and effort. Is it easy to carry only 2 or 3 as opposed to 50 or not? Of course not. Yes. When you bring with you 15 books, this means that you may need to pay for others to come with you, or you may need to go and come several times, or you may need to bring something to help you to carry all of this stuff. You will pay more, or you may need to carry all of them, but that means that you will walk very slowly until you arrive to the same exact location, correct? So miss penalty, yes, increase the block size, that's fine. But unfortunately, each time you miss, it will be hitting you a lot. The miss penalty will be huge. So we understood the compulsory miss and how we can solve it, or one of the examples that we can solve. Another one is the conflict miss. What is a conflict miss? It's just a collision, and this is expected since we have direct mapping, or we have a mapping between large place and small place. So multiple memory location map to the same cache location. Different students are mapped to the same parking spot. So with high percentage, you will have a collision. You would like to park at the same time that other students who live in the same place, who are sharing the same spot with you, that will need to park at the same time. How we can solve that? Of course, increase the parking lot spots or increase the cache size, which is not always feasible. Another important thing that we can do, increase the associativity. We will introduce later on what is meant by associativity and how using the associativity will help in this particular case later on. But for now, just take it as it is. that we can actually increase the associativity, and this will help with the conflict miss. But as we will see later on, that this may increase the access time a bit. Another thing is called the capacity miss. What's the capacity miss? It's just the problem with the capacity, because the cache is not big enough to contain all of the cache blocks for this particular situation, for instance. How I can do that? Increase the cache size. One of the options, but it's not always, again, feasible. Also, another solution that add another level of the cache. So might have level 1 cache, level 2 cache, level 3 cache, and so on and so forth. This might also be helpful in this situation. So now we have mentioned that increasing the block size might help in some situations. Let's go deep a little bit to see how this is affecting positively or negatively our situation. So we have agreed that increasing the block size will basically enhance the miss rate or reduce the miss rate. Okay, that's fine. But there is a limitation here. If I am increasing the block size, but my cache size is limited or is fixed, then I will face problems. Meaning, you can think of this that way. You would like to design a hotel with 100 rooms. If you will include 10 rooms per floor, so that means that you need 10 floors, correct? But you don't have an elevator, or you don't have a budget for an elevator. So this might not be good. So you have decided to increase the block size, meaning increase the number of rooms per floor, correct? Which will help in this particular situation. So one said, okay, that will be great. So why not to have only one floor? And then in this one floor, you will have 100 rooms. But that guy forgot an important issue, that there is a limitation on the size that you need to build your hotel in, correct? There is a size. Suppose you have 5 acres, 6 or 7 acres, whatever, there is a limitation that you can't do that. Correct? So you might increase, yes, it is helping to reduce the number of floors, but to a certain level. You can't go beyond that, because unfortunately it will affect negatively. They might say, okay, if you will increase the land, then you have to pay that much. Then you are actually losing other stuff. Here is also the same. If you are increasing the block size, that's good. It is decreasing the miss rate, but to a certain extent. As soon as my block size will be comparable to the total cache size, that's no good. Because this will reduce dramatically the number of floors. And if it decreases dramatically the number of floors, the miss rate will go up again. Because suppose that you have only 2 floors and in each of one floor will be 50, then this will increase the miss rate, because each time you just need to go to either this floor or that floor, correct? Of course, you will miss, the miss rate will increase. And we will show you this by examples later on. However, if I am increasing the block size and there is no limitation in my total cache size, of course, increasing the block size will reduce the miss rate. So now I have 10 rooms per floor. Next, I have 20 rooms per floor, but 20 again multiplied by 10. So now I have 200, 300, 400, and so on. Increasing the number of rooms would be good if there is no fixation in the total number of rooms that I have. But if that number is comparable, the number of rooms per floor and the total number of rooms in my hotel, this is an issue. This is a problem. Then, unfortunately, it will affect negatively the miss rate. So again, miss rate goes up if the block size becomes a significant fraction of the cache size, because the number of blocks that can held in the same size cache is smaller, which will increase the capacity miss in this case. Also, the other drawback is larger miss penalty, as we mentioned, because when you increase the block size, you are basically increasing the miss penalty. Each time you are going to the library, you have to bring 15 books with you, for instance. If you go to the library, you have to bring 20 books with you, 30 books with you. Of course, the more that you increase, the more effort that you would pay in this particular case. Let's go deep a little bit with this nice graph. It shows you, suppose that your total cache size is 4K, 16K, 64K, 256K. And suppose this is my block size bytes, 16, 32, 64, 128, 256, and so on. So with increasing the block size, I need to check my miss rate. If my total cache size is 4, at the very beginning it decrease, but then after a certain particular situation, when that size is close to the total size, then things will begin to be dramatically the other way around. My miss rate begin to increase again. And this is, of course, is not as noticeable as you can see from here, which is 256, because 256 is not very close to the 256 kilobyte as opposed to the 4 kilobyte. And that's why it decreased at the very beginning and increase later on. So generally, if I have a miss rate, the block size usually decrease and then increase. This is something that is expected. How about the miss penalty with the block size? When the block size increase, I have to pay more, yes? Because when you carry 2 books, it's not as you carry 3 books, it's not as you carry 4 books. Usually when you increase the number of books, you actually have to have more efforts and so on and so forth, correct? That's usually the miss penalty increasing with the increasing of the block size. So now I have 2 parameters. We thought about combining these 2 parameters in just one parameters, which we call average access time. As the average access time is not but the hit time plus miss penalty multiplied by miss rate, meaning this multiplied by this will give you this plus the hit time. That's why this is have this kind of situation in this particular case. Suppose that we have here an embedded microprocessor, example, intensity fast math, that uses MIPS architecture and simple cache implementation, 12-stage pipeline, split the cache separate instruction cache from the D cache, and each 16 kilobyte has 256 blocks multiplied by 16 words per block. By the way, just as a question, if this multiplied by that will give us this? So here, this is word and this is byte. So you might just need to multiply here by 4, it will give you this in byte, or divide this by 4, it will give you this in word, and so on and so forth. And the cache is just write through or write back. So let's see that example. It shows you here that this is the cache. Again, we have the tag and we have the validity bit, and we have here 256 entries. So you have 256 floors or 256 blocks, but it didn't give you like how many of these, for instance. It didn't show you here how many of these, just showed you that each one is 32 bits. And if each one is 32 bits, so I already knew that this can be divided till to 4 bits or 4 rooms. And in this case, I need 2 bits to basically specify the room number, and that's why, or byte offset. That's why I have this very first 2 bits to specify the byte offset, or as we mentioned, just the room number. Then now I have to specify that I am in this word, not in the other words. I don't know how many of these, however, the answer here is 4. So I should expect that I can hold actually till 16, yes, as an example. However, this is given here, in this case, 16 words per block, correct? But if it is not given, I should expect that from there, because 2 to the power of 4 is 16, so it can hold up to 16 words, or anything between actually 8 and 16, correct? any number between 8 and 16, but in this case it is 16 because we already mentioned that. So now I have specified the room number. Sorry. I have specified the word location by this. Now I need to specify the floor number. The floor number 256, so log 2 to 256 is equal to 8, and that's why I have here 8 to specify the floor number. So now I have specified the location. Anything after that, it will be here 18, which is basically the tag. So it is 32 minus 8 minus 4 minus 2. It will give you 18, which is the tag. And as we mentioned, the tag might have the information as an example like date, time, and so on and so forth. Then I will be able to specify you among all of the other guests who were in the same room earlier. So how to handle the cache misses, for instance? We have read misses and we have write misses. With the read misses, just as we mentioned, we need to wait, just stall the pipeline and then bring from the lower level, let's say the main memory, to the next in the hierarchy, for instance, the cache, and just send the requested word to the processor and so on and so forth. How about if I have write misses, meaning I try to write to an address that is not already contained in the cache? One option is to do exactly the same thing that as I did in the read misses, just install the pipeline, fetch, and so on and so forth. But it might involve, of course, evict of the dirty block if using the write back cache. But I can also do something called the write allocate. And write allocate, I just write the word into the cache, which update the tag and the data in the cache, and no need to stall, no need to worry about the other levels in this particular case. Or there is no write allocate, meaning I will just skip the cache write. I will not write anything in the cache. Instead, I will go to write that in the memory. But in order to write in the memory without waiting, I just need to write in the write buffer in this particular case, which of course eventually will be in the next level. And I won't need to stall unless the write buffer is full. Otherwise, I just need to proceed without any problem. But in this case, if I will skip the cache, I just have to invalidate the cache block, since I have to invalidate since it now holds already an old or stale data. So just as a summary, where should I write the result of a store? If that memory location in the cache, then I just send it to the cache, or I send it to the memory right away with write through policy, or I don't have to do that. I just send it when needed, wait until we kick the block out with the write back policy. If it is not in the cache, then I can do the write allocate policy as we have indicated, locate the line and put it in the cache, or the no write allocate policy, which write directly to the memory without any allocation. So we need actually to highlight a little bit the situation when I have a multi-word block considerations, meaning that now I have multi-word block, different block in the same floor or in the same block, many of these. We mentioned in this situation, the miss penalty is high because I have to wait all the way until I fill all of these stuff, though I just need one of them, for instance. Suppose that I need this. Unfortunately, I need to wait for this to be filled out, and then I will be able to access the data. But the question is, okay, can we enhance this strategy? Can we enhance this process? They came up with a very nice idea that's called earlier start. Meaning, suppose that I am requesting the data that is here, but it will first fill this, next this, and then this is appear. And as soon as it is available here, then I will be able to use it. It's called early restart, meaning as soon as the data that I would need available, please go ahead and use it. But there is a problem here that suppose my data is here. So this means that actually I also need to wait all the way until I arrive to this particular thing, which is basically the very last one. Correct? So this means that always I have to wait a lot. Can we enhance the process? They said, yes, there is a very nice idea. It's called requested word first, meaning I will always request whatever I need first, even though I this. So this means that this will come first, and then I will fill out all of the other ones. But as soon as this come, I will begin to use it in the process. So either earlier start or requested word first, which of course requested word first would be much better in this case. There is also another situation that's called non-blocking cache, which allow the data path to continue to access the cache while the cache is handling an earlier miss. But how about write? This is with read misses. How about write misses? Can I do the write allocate? Can I do the write allocate in this case with multi-word write allocate, meaning that I'm just updating the cache, update the data, update the tag of the cache, and that's all. But this has a very interesting problem. This is my multi-word block size, and suppose that I would like to access this one, and I have updated this one with the write allocate. So I have updated this one, but unfortunately, this has all the information, this has all the information, all the information, all the information, all the information, and this only one that has new information. Is this acceptable? Of course not, because this is just garbled data. It will confuse us and we will not know which is which one is new, which one is old, and so on and so forth. And that's why we can't use write allocate in this case, and we must fetch the block from the memory and pay the stall time. I just need to wait until I update all of the scenarios in this case. We mentioned that we will use the dynamic RAM for the main memory, and suppose that it has a fixed width and connected by fixed width clock bus, as we will explain later on. Also, suppose that I have a cache block that needs 1 bus cycle for address transfer, 15 bus cycles per DRAM access, 1 bus cycle per data transfer. And for instance, we have 4 word block and 1 word wide DRAM. In this case, the miss penalty will be 1 plus 4 multiplied by 15. So this plus this 4 multiplied 16 plus 4 multiplied by 1. It will give me at the very end 65 bus cycles. So my miss penalty right now is 65 bus cycles. My bandwidth is just the 4 word multiplied by 4 bytes, which is 16 bytes. It's 16 bytes divided by how many cycles do I have at the very end, which will give me 0.25 bus per cycles in this particular case. So with this DRAM, interestingly, it's organized as a rectangular array, as we will explain later on. And the DRAM, I can access actually the entire row, or with the burst mode, I can actually supply successive words from a row with redundant latency. And this also will be covered in details later on. Interestingly, we have something called DDR, which is double data rate. So how I can double the data rate? A nice idea, by transfer on rising and falling the clock edges, then you will actually doubling the data rate. How I can do a quad data rate? QDR. With the QDR, you will just separate the DDR inputs from the outputs. So the DDR by itself is rising and falling edge clock. You are transferring the data, but you separate the input from the output. So actually you have, in this case, quad data rate. There are other performance matrices that will be covered as well, with the row access strop and column access strop, and some basically expressions here in terms of latency or access time and cycle time and bandwidth, which we will also hopefully introduce in details in the next slides.